Okay, let's talk about number 4 a little bit. So number 4 I talked about in class a tiny bit already, but let me review. So in this case, the topological space we're looking at is the space of bounded functions on 0, 1 into R. So functions that take values from 0, 1 and map into R. So your ordinary real-valued functions. And the description of the metric for these is defined in the text. So then we define this function from that topological space, X, into the topological space R, and this map tells us how we define our function from X to R. And for any point in X, and every point in X is a bounded real-valued function. Every one of those real-valued functions, we map it to R by just evaluating it at 1. So each of those functions is defined on the interval 0, 1, and we just look at the function value at 1. So think of it this way. You've got your topological space. Here, this is X, and you're taking points in that space. Points in that space are functions, and you're mapping those functions. For each function in that space, you get a real number. So you take a function and you spit out a real number. This is often called the evaluation function. And we want to show that this is continuous. Now we have a definition of continuity between two metric spaces, and I've modified it here so that it reads exactly the way we need it. So if we have topological space X, that's defined above, and a metric, and another topological space, well in this case it happens to be R, the real numbers, and dy, and this is the ordinary metric. So these are two metric spaces. We have a map between them. Capital F, it goes from X to R. Oops, and that should be a capital F. Capital F is a continuous function at little f, that's a point in X. If for any epsilon greater than 0, there is a delta greater than 0, so that, well, essentially the pre-image of an open ball contains an open ball. The function f is continuous if it is continuous at f for all f in X. And we want to show that this is a continuous function on the whole topological space. So we're going to pick an arbitrary point in X. We're going to let epsilon greater than 0 be given. And we're going to consider this thing. We have to show that that thing contains an open ball. That's equivalent to saying if I can find a delta greater than 0 such that this open ball is contained in this pre-image, I'm done. And my suggestion is to let epsilon equal delta. And then if you pick any other point in this open ball, this is an open ball around the point F of size delta. And we're going to let delta equal epsilon. If we pick any other point in that ball, maybe I should say G can differ from F by at most epsilon. That is, this is the definition of our metric in the space of bounded real-valued functions on 0, 1. And since F and G in this case, this G and this F, are supposed to be in the same open ball, they're within epsilon of each other, now that I've said epsilon is equal to delta. That means that, well, if you remember how we think about these, if this is my F, well, I really should just do it on 0, 1. Let me erase that. If this is my F on 0, 1, then G has to be a function that is well within some margin of error, right? Some epsilon distance from there. In particular, the difference between the function values of these two functions at any given point, or the function values of these two functions at any given point, can't differ by more than these sort of error bars here. And what does that mean in our case? That means f of 1 and g of 1, the difference between them is less than epsilon. And I really should have written f of f minus f of g is less than epsilon. And what does this mean? That means that all these points g, the image of these points g, are in this epsilon ball. It's equivalent to saying that the this epsilon ball here is contained in this pre-image. Now that's not quite totally the formal proof, but it should get you started thinking, or at least give you some grit to start asking me questions about it. I want to do one more quick